Here's a small design decision with enormous long-term consequences.
In the LinkedIn resume example, region and industry are stored as IDs, numeric identifiers that point to lookup tables rather than as plain text strings like Greater Seattle Area or Financial Services.
Why? What's wrong with just storing the string?
Think about what happens when you store the human-readable value directly.
Every user profile in Seattle stores the text Greater Seattle Area.
If the city's official name changes, or you want to display it differently in a new locale, you have to update every single row that contains it. Thousands, potentially millions of rows. And if some rows have a typo Greater Seattle Area, you now have inconsistency permanently baked into your data. An ID, by contrast, never needs to change.
Only the information it points to changes.
Update the name in one row of the regions table, and every profile that references that ID instantly reflects the new name.
No data migration. No risk of inconsistency. The book identifies several advantages to this approach: consistent style across all records, no ambiguity for cities sharing the same name, easy updates in one place, localization support for translating display names per language, and better full-text search through a centralized index.
This principle, removing duplication by referencing shared data through an ID, is the core idea behind normalization in databases.
Normalization is not just a performance technique. It's a correctness technique. Duplicated data is data that can become inconsistent. But here's the trade-off: normalization requires many-to-one relationships. Multiple users all pointing to the same region ID.
And many-to-one relationships don't fit naturally into the document model, they require joins. That tension is at the heart of the relational versus document debate, and it's older than NoSQL by about 40 years.
The debate over how to handle many-to-many relationships is not new.
It was already raging in the 1970s, and the outcome of that debate shaped every database system built in the half-century since. In the 1960s and 70s, IBM built a database system called IMS, the Information Management System. IMS used what's called the hierarchical model, all data stored as a tree of nested records, similar to how JSON documents work today.
Like document databases, IMS worked beautifully for one-to-many relationships.
Like document databases, it ran into serious trouble the moment many-to-many relationships appeared. Two competing solutions emerged to fix the hierarchical model's limitations.
The first was the network model, standardized by a committee called CODASYL. The network model generalized the hierarchy. Instead of each record having exactly one parent, a record could have multiple parents. A student could belong to multiple courses. A product could appear in multiple order lines. This sounds flexible, and it was. But there was a catch: to access any record, you had to traverse a fixed access path through the network. You had to know in advance which path to follow. If your access patterns changed, new queries, new features, you had to rewrite your access path code. The network model gave database administrators enormous control and gave application developers a maintenance nightmare. The second solution was the relational model, Edgar Codd's proposal.
Instead of nested records or access paths, the relational model laid all data out in open tables.
Any row could reference any other row by value.
And instead of telling the database how to navigate the data, you simply described what data you wanted. The database's query optimizer figured out the most efficient way to retrieve it.
The relational model won. Not because it was fastest.
In fact, early relational databases were slower than CODASYL implementations. It won because it was easier to develop applications on top of. The query optimizer did the hard work, and developers could change their queries freely without touching access path code.
Document databases today are revisiting the same trade-offs IMS faced. The same problem, many-to-many relationships, still needs to be solved. Let's look at how document and relational databases compare today, not just in terms of structure, but in terms of the trade-offs that actually affect the teams building on them. The main arguments for the document model are three. First, schema flexibility. Second, better performance due to data locality, related data stored together, retrieved in one read. Third, a closer match to the data structures applications actually use, reducing impedance mismatch. The relational model counters with its own strengths. Better support for joins. Clean handling of many-to-many relationships. Easier to query data in ways that weren't anticipated when the schema was designed. A key distinction the book draws: document databases are often called schemaless, but that word is misleading. A more accurate term is schema-on-read. The structure of the data is implicit, the code that reads the data is responsible for interpreting the structure. Compare this to Schema-on-Write, which is what relational databases use. The schema is explicit, and the database enforces it on every write. Invalid data is rejected at the point of insertion. These are not just philosophical differences. Schema-on-Read is advantageous when your data structure is heterogeneous, different records have different fields, and the format is changing frequently. Schema-on-Write is better when you want guarantees. If data is in the database, it matches the expected shape. Here's where it gets interesting: the two models are converging. Most relational databases now support JSON columns. PostgreSQL and MySQL both let you store and query JSON natively. And document databases like MongoDB added join capabilities. Neither model is pure anymore. But convergence doesn't mean they're equivalent. The underlying architectural choices, how each model handles relationships, how each enforces consistency, how each scales, still differ in ways that matter. And those differences become especially visible when the data is highly interconnected. That's where graph databases enter the picture.